rational functions. Again, you see that word rational, I see the word ratio in rational, which says what, fraction? It's not a fraction. Now, your textbook says, write this as, for a rational function, ratio, fraction, r of x is equal to, they write as a fraction, as this. P of x over q of x. Oh my goodness, we're supposed to graph something like that. It's going to be in fraction form this time. And we know by this point that the q of x, the denominator, cannot be what? 0. Now, can someone tell me before I show you an example? What, even at this point, when they ask me to sketch a graph of something that looks like this, what might tell you right now, based on some things we know, that might say, Professor, yeah, a graph of something like this, a rational function that takes this form, it may jump on you. It may not be nice and well behaved, and they use the word continuous in math. Not nice and well behaved and continuous. It might be discontinuous. What might make a rational function discontinuous? Give me something. What might show up that has not shown up on polynomial, but now it's showing up. It may say, whoops, this graph's a little different. It's discontinuous. It's not nice and continuous. Yes?
If there's something like x minus 3 in the denominator.
Okay, here we go.
If there's something like x minus 3 in the denominator, would it be that there's a further hash?
I heard what you said. Could you write, give me an example. Give me an example of a rational function based on what it should look like. It should look like something on top, polynomial maybe of some sort, and on the bottom, another polynomial. So what might that be? Let me show you. I may not be explaining it correctly. R of x, would you guys agree? I was making this up real quickly. They're saying, please now, we're going to look at these. They're called rational functions. They're in the form of a fraction, ratio. Now, can anyone tell me right quickly what x values could I not let that graph take on? 2 and what? -2. That's what makes it not the same as polynomial. Polynomial took on all the values for domains. Negative infinity through positive infinity. This thing does not. In fact, this tells me right quickly if this were the problem, out to the side here, x cannot be plus or minus 2. Now, when I start graphing, does anyone have an idea where I jump into all the routine to follow? What might you have to do on a graph to show? Don't use 2, and don't use -2. And somehow you're trying to show someone on your graph, I can't use those 2. What do you think you'd have to do to show someone that you can't use those 2? You can't use positive 2, you can't use -2.
Be good enough.
There we go.
Well, x is be good enough, or is it
Sort of. So what is going to make this graph so different? Yes?
There's gonna be a gap.
Okay, there could be a gap, absolutely, or it could be a hole on the graph.
Yeah, and like 2 different star points.
It could be. But something's going to be strange about this graph, because you've got to show someone I cannot use where x equals 2, and I cannot use x equals -2. So I've got to somehow indicate that on my grid to graph this thing. We'll graph one like this here shortly. What I want to do before I jump into one like that though, let's go back to here and ready. I'm going to give you a most simple rational function out there. This one. Let me start with it first. That's a rational function. 1 over x. P of x over q of x, fraction. On the handout, I think maybe this one was on the handout way back on the parent functions. I think it may have been. Some books, some textbooks will call this the reciprocal function. Like a reciprocal working here. 1 over x. If you graph it, some students may recognize already what 1 over x looks like graphed. And you could do a table. There's nothing wrong with the table. But does anyone in my class have an idea what 1 over x, reciprocal function, rational function, looks like if you were to be patient and you graph it. Yes?
Is it one of those ones where it starts out like higher and it goes almost to the x-axis?
Hang on,
but
hang on.
doesn't touch it?
You are describing, maybe Professor, does something like that.
Yeah.
I'll place arrows on you here. Might there be another piece? I didn't form a table here, I could do it through a table. Does anyone have an idea, is there another piece besides what I have right now?
It does look like the same one, but in the bottom left quadrant.
Okay, this quadrant here, they call it quadrant 3. On the grid, this is quadrant 3 here, another one there. And those do not touch either axis. That's the graph of that. You say, Professor, no. Really? That's a graph of a reciprocal function? And you could, I'm not gonna do it for you here, though, you could do this, say, Professor, can I do this to get that graph? X, 1/x, and try maybe a few numbers here to work with. Why not? And just at random, throw in some numbers. As many as you wish, and go through and say, oh my goodness, this is -1/2. This is -1. This does not exist. There, 1 here and 1/2 here. These are my initials here. Does not exist. Then you can plot those points and start connecting, or add more to the table. You'll get, as described, this. One piece in the quadrant 1, the other piece down in quadrant 3. And that's the way it looks. That's a rational function. Now, is it connected? Are the two pieces connected? No. So they use the word discontinuous. It is discontinuous. A discontinuous function.
But the domain and the range are equal.
Beautiful. Now, let's go check out the domain and the range of this most basic rational function here, guys. It's discontinuous. Can anyone tell me where they may specify, where is this red graph discontinuous? At what point? No, where does it happen that they are separated? At the origin. Right here at x equal to 0, it's discontinuous. Which we thought probably at the very beginning that was where it's undefined. Right? If I replace x by 0, it's undefined there. That's where it's going to be discontinuous. So it's discontinuous here at 0. One piece is here, one piece is here. They're split up. They're not connected. Discontinuous. That's the way it looks. Now, domain and range, I heard. Guys, the domain on this red graph is negative infinity. Absolutely. Up to 0. Union 0 through what? Infinity. Range, the up and down. How would you describe the range? Same thing in this case. Negative infinity up to 0. Union 0 through infinity. There's your domain, there's your range. It's discontinuous. At 0, splits up into 2 pieces. And that's where it looks. And that's one of the most basic rational functions out there. Now, we have some to graph that are not that basic. Okay. Before I get into some of those from the handout, and Andrew has been helping me out a lot, I may ask him to write some, or read some of those steps for us to follow. Before I do that though, our feet. Take just a few seconds. I want someone to tell me something about this rational function. Then we'll look at the handout. Look at that rational function. Looks like it's u of x over q of x. And I say graph it. Now, let's get a little conversation going, then we'll get to the handout. See what this is all about. Anyone see anything going on here on this one?
X cannot be.
Well, X cannot be two. Love that, tell me more. And I actually wanna graph this one. And not we just take, more like just take. Anyone?
There's only
What's so
one.
unique about this rational function?
The factor of x minus two cancels out with x minus two and then top is x two minus four factored into x minus two and x.
She's in professor. Part of this will factor. That x squared subtract 4 on top factors into this. X subtract 2, x plus 2. We all would agree with that. And then she's telling me, professor, these two factors cancel. So that takes your rational function in simplified form down to merely that. Is that true? Now please tell me from across the street, what would x plus 2 graph into? Is that a straight line? Is it linear? X plus b? We're into now a line, so this, it's gonna graph into a nice straight line? Professor, I thought you said something strange supposed to happen on these rational functions. But right now, looks like we have, if you want to use the mx plus b slope y-intercept method, or do a table, or do x-intercept, y-intercept, lots of ways to get that line. Guys, I see myself, if you should set this equal to 0 and solve it, you get -2. So that's your x-intercept. So you quickly say out here, the x-intercept is here. You're going to find the y-intercept, you're going to use intercepts to do this, replace x by 0, and you get a positive 2. It's here. Connect those, and do a good job here before I get to that handout. So, okay, professor, here, connect them, and you get a nice straight line. And you're at UCLA or USC, you say, my gosh, there's the graph of this. Does anyone, or will we accept that? Accept the graph? Or is there, sure enough, I use the word strange, is there something strange going on this rational function, as over here it's split up into 2 parts? Is there something strange happening here? There's something strange happening here. That's what the difficulty is with these rational functions. Yes?
Since x cannot equal 2, should it be an open point on the line?
X cannot be 2. So that means when you go out to 2 here, right here, and look on your graph up here, it's not supposed to exist. A student gave me early, he said, x cannot be 2, professor. So I gotta show somehow that graph at x equal to 2, that does not exist. So wait, if it did exist, where would I be up there? What number is right here? Out 2 of what? Is that 4? Help me out. Is that 4? If I replace this by 2 plus 2, is that 4? So right here is a point. Right now, I'm going to place it right here. With coordinates out 2 of 4. But it's not supposed to exist. It's undefined. Can anyone tell me what I might do on that linear function, straight line, to show, hold on, professor, show that point is not supposed to be included? What do you think I'll do? Phil,
An open circle.
there you go. They call it a hole on the graph. Open circle. Now you have a nice straight line with a hole on it. And the hole is at out 2 up 4. And that's your graph. Okay, so strange things will start happening. strange things. So strange, I'm gonna just work a couple of these from your handout, because they can get really, really, really strange. Got any concerns here? Okay, I would've thought as a student, maybe, professor, after you did this business, and you got down to here, it should be that nice straight line. But then I forgot, you can't let X be 2. There's a hole on the graph. Andrew, read the first one there, or we're gonna read through the steps, but also, tell me what the first example down there at the bottom is.
It says, Rx equals x minus 1 over x squared minus 4.
Like that. Okay? Now I'm gonna have him to read the steps for us. Mr. Park, put that, open that door back if you could. They always in this room so warm. You guys think it's too warm in here? Now, what's step 1?
Step 1, find the domain of R of x. Do not cancel the factors in step 1.
Okay, just that. Now look at your function given to you and name the domain right now at this moment. Don't do anything to it. And guys, I think if I want to answer this, the domain would be x cannot be plus or minus 2. Now, if you want to put that in interval notation, go for it. Plus or minus 2. True. Step 1's done. By the way, I'll have these steps typed up on the quiz or exam for you. So step 1, I'll have typed up, find the domain. Now what's step 2, Andrew?
Step 2 is simplify it. Write R of x in lowest terms.
Hang on. Yeah, let me do that first. Let's go ahead and factor that denominator. And now we say that's in simplified version, and I give you partial credit to do that. What's step 3?
Oh, okay. Step 3, name the intercepts x and y of the graph.
Okay, I'd like to know where the x-intercept, when I finally get to the graph, will be, and where the y-intercept will be. Guys, remind me, even on the work we've done in class before, how does one find an x-intercept?
Y equals.
You said y equal to 0, which means this is the y here, r of x. If I set that equal to 0, you have this. And you'll leave it as x minus 2 times x plus 2, you could. And you gotta solve that. You set the function equal to 0. We'll always do that. I would suggest, it's up to you, you can multiply both sides by that denominator, or you can do a cross multiplication. Some students will say, Professor, can I write that 0 as 0 over 1 to make it easy on myself? Of course you could. And some students will do this. So let's quickly multiply these two together and these two together. Cross multiplication. All it's going to give you is this. That's all it's going to give you. Which means when I solve for x, I have discovered the x-intercept. I'm going to write as an ordered pair, 1, 0. These things are lengthy. That's why I'm just working a couple of these today. Now he said, Professor, also find the y-intercept. Easily done. That says go back and replace all the x's by 0. Guys, if you want to go back to the original, you could, or go back to step 2. You could do it either one. I'm going to go back to the original. Looks like it might be a little bit easier. Replace it by 0. 0 subtract 1 over 0 squared subtract 4. I think that's a positive 1/4.
Yes.
I'm writing as an ordered pair. It looks much better. That's my y-intercept. You get all partial credit for this. We don't have the graph yet. He's sort of leading me into finding the graph. Andrew, in step 3? Or step 4?
Step 4, determine the vertical,
Asymptotes? Oh, I have not even used that word.
Yeah. Determine the asymptote, if any, of the graph.
Now, I have not yet identified what that strange word asymptote is in math. Guys, now they're asking me, are there some, separation points on this graph when I get to it? They want you to name, where might my graph be separated? Back here on this one, it looked like it was, where was it? At zero. I got one piece on this side of zero and one piece on this side of zero. That's where the separation took place. This one only had a hole on the graph, that's okay. If you want to think they know at what? 2 points. Do you think there'll be
Plus
a
minus.
separation?
Plus minus.
Plus minus 2? Absolutely. Andrew, did I point out something there to help you find those? Did I have more to read there? For vertical asymptotes?
Yeah, it said note, set denominator equal to 0 and solve.
Set the denominator equal to 0 and solve. Right, that's my denominator. When you solve this, set it equal to 0, yeah, you get these. So when I get to the grid, I've got to show, that says vertical. I think you use the word vertical. Vertical asymptote. That means there's going to be a vertical line placed at those two separations. Woo! Try the next one. Number 5.
Step 5, determine the horizontal asymptote if any of the graph. Note the horizontal asymptote will describe end behavior of the function.
Now, hold on a second. Now they're saying, oh my goodness, besides the vertical line, some of these will have a horizontal line also. That will help guide you and show you the end behavior of the graph. I wish these things were well behaved. You can see, I hope you see right now. Professor, let's go back to polynomial. Let's go back to polynomial functions. End behavior, cross touch. Nope. These are not well behaved. Now he's asked me something like this. Professor, find the horizontal asymptote. And we're right. But, Andrew, did I give some rules to follow as you try to find what this is?
Yeah, to find the horizontal asymptote, we will use the end behavior r of x equals 1 over x.
Hang on. Let's go back to 1 over x. Anyone tell me out here on the end, how would you describe the end behavior of this red graph out here? In other words, this, the limit as x is approaching infinity of that function 1 over x is what? As you drag that red graph out this way forever, what's it doing? It's getting closer and closer and closer to what? 0, the x-axis. By the way, guys, that's the end behavior. I'm going to throw this in if I need it. But on the other end, negative infinity, same function, you'll get 0 again. And that's the end behavior that Andrew's telling me of this parent graph. Now, can I now take my function, use that knowledge, and find where is the horizontal asymptote going to be located, or the end behavior here on this one? By the way, where is the horizontal asymptote assumed to be on my parent graph? Where's my horizontal line that does like a separation? Is it the x-axis? Does the x-axis sort of split this graph up? And does also the y-axis. So he's talking about a vertical asymptote, this is vertical, and he's talking about a horizontal. We have the vertical out of the way over there. Now I'm looking for the horizontal. Try my best to use this distance. But where is it located? It's the x-axis back on that parent graph. That's my horizontal line that does that separation. Guys, here goes. And I'll give you a shortcut later on. Let's go back to my function. Ooh, here goes. Scan the function and tell me what's the highest exponent you see as you scan the entire function. What's the highest exponent you see? That's first thing. We're going to identify the largest exponent in the entire function. Check out the numerator, check out the denominator. What's the highest exponent altogether that you see?
X squared.
A 2. Is it a 2? X squared. After you identify that, you're gonna go back, this is a little calculus, and divide all these by that x squared. Watch what's gonna happen. Okay, on the side here. This is trying to find this strange horizontal asymptote. You got x over x squared. Okay, mark it here. We got minus 1 over x squared here. My function, x squared over x squared. Everything's being divided by x squared. And minus 4 over x squared. So first you identify the highest and divide every term in your function by that. And then simplify the best you can. Guys, if I simplify this at this moment, I think one of the x's will cancel here from algebra. And give you what? 1 over x? Now, 1 over x squared is a little strange. I'm going to rewrite it for a reason. 1 over x squared could be, there's no canceling, could be written as, for a reason, it's coming up, 1 over x times 1 over x. It's still 1 over x squared. Down here, they cancel all together into a 1. My second term, for a reason, 4 over x squared, we'll rewrite it as 4 times 1 over x times 1 over x. Woo! Wonder why I did that with the 1 over x to short up as much as possible. And
Because they cancel out.
why?
At the bottom.
Tell us why. I'm staring at it.
Well, it's the equals.
We've already established this.
Yeah.
And when you see a 1 over x, and you're trying to find the end behavior as x gets large, all those are 0. So if you can do that business, a little algebra, and change the form, which I did, every time you see a 1 over x, based on that over there, you get to do this. You say, wait, professor, this is 0. This is 0. 0. There. And there. And then do your calculation. Which in this case is not too interesting, because I think you end up with a 0 on top, numerator. And down here, guys, what is that? 1 subtract, what, 4 times 0 times 0, that second term will drop out to a 0. 4 times 0 times 0. And I'm going to end up with, after all that effort, that. Is that what I end up with? After all that effort. Which tells me when I get to the grid, where is my horizontal asymptote? If it says at 0, where is it located on this graph when I get to it? The x-axis. Again, just like on the parent graph. Now later on it'll change. But right now it's on the x-axis, it's at 0. Lord, that's the horizontal asymptote. We go back right here. This is y, guys. Y is equal to 0. X-axis. We gotta get accustomed to this. We're gonna take a break in 5 minutes here. Andrew, tell me what's next. I may skip that and just go right now. I think I have enough to get a sketch.
Step 6, determine the oblique.
Oh, stay away from that today. Oh my goodness, no. No oblique. No. Oh, we're going to, if we get this enough here, we don't need oblique. If you see oblique, I have to hold on that tomorrow probably. Okay, guys, we got 5 minutes. Now, can I, with your help, put all this business together and get a graph? And I will tell you ahead of time, your graph's going to be split up. Now, let's try in 5 minutes and see what that graph looks like. I'm having a brand new cleaning a room here. And we'll take a break here. Guys, here goes. I'll get your help. Go to the grid. Keep in mind, these are so intense, I'm just doing one more today. After the break. Let's pick up some items here, guys. What do we have? That would help. Well, the first thing I see is, I know the domain, I know this. Let's pick up the intercepts. We have x-intercepts at what? What is it, 1, 0? Yeah, so about 1 out here. I'll mark that. That's something on my graph. And I have 0 up 1/4, that's my y-intercept. One here is a reference. We'll put 1/4 right there, barely above the x-axis. 1/4. Got that, done. Vertical asymptotes, Andrew, we finally decided on these two. So it says go out to 2, -2, which I will. Watch carefully, guys. Some of you guys may have experienced rational functions before, but they can be tricky. I'm right here now. What do you think I'll do at 2 and -2? And the key is vertical. Draw a vertical line. Call it vertical asymptote, draw a vertical line. Try to do it in blue here. Got one there. And one here. There's my vertical. Now give me partial credit, lots of partial credit. Horizontal, we finally decided after all that business over there, it's the x-axis. Do that. We'll try red. So this is the horizontal asymptote. Step to the side, if you guys can see that red is a little light there. You guys see all those colors? Please tell me, do I have all the information we have over there on this? I have the two vertical, the horizontal, I have the x-intercept, I have the y-intercept. Now we're ready to graph. And then we'll figure it out. Next, Professor, how many pieces are there? You said it's going to be separated. So what's going to happen? One piece of the graph is going to be to the left of this blue vertical. One piece is going to be caught between the two verticals. And there's an additional piece over here. There's going to be 3 pieces to this graph. And they will be separate. Something to the left, something in between, and something to the right. Now, you can plot points, additional points to see what is happening. But does anyone have an idea? I think a good way to do this. What the graph may look like on the left of -2. And maybe it's difficult to see right now. Does anyone have a guess? Before we close it out here. Okay, let's do this. Let's plot a point. So on the grid, I'm out to the left of -2, guys. Let's try, I'm gonna put X and Y here. I'm gonna try -3. Like that, what's going on out here? Where are you gonna put it, Professor? Put it back here in the original. Replace these X's by -3. Help me out, guys. Replace X's by -3, I think you get -4/5. Do I? If I substitute X with the -3, is that -4/5? I think -4/5. That says, Professor, to the left of -2, you tried -3, you're down here somewhere. The screen will work for me. You're down here. -3 down 4/5. Now, based on that, guess what? I can now see where my graph is over there. It's got to follow those asymptotes. That's why those asymptotes are there for me, the red and the blue. It's got to look something like this. And not touch that vertical and follow the red. That's why those asymptotes are there. You get to follow each one. You can't touch the vertical. Why not touch the vertical? Where did that vertical come from? Did we set the denominator equal to 0? Yeah, that would make it undefined if I should touch it. Now, in between, does anyone have an idea, what does the sketch look like? And I've got 2 points to work with here, thank goodness. Between. What do you think the graph will look like when I draw it? I gotta connect those 2 points. Any idea? Go for it.
It will start from positive infinity.
Whoa, hang on, I didn't plot points. He's telling me,
at -2.
like this,
Yeah.
hang on. And don't touch that blue. And then what?
And then cross the x-intercept 1.
Right there.
And down to -infinity.
Oh my goodness. Now, what would help most students would be to go to a table, professor, and plot more points. I can tell for sure. Any guesses, or I don't really want to guess myself. Now I'm out to the right of 2 to finish this thing up. Out to the right of 2, I am going quickly. I'm gonna try 3, so I can see where it is. Like in 3 here, guys, I think you end up with 2/5, 2/5. So that says out 3, out 2/5. Let's say 3 is right here. Up 2/5, so this is right there. Is that enough now to see what's happening on the other side with the help of the asymptotes? Got to not touch the blue and follow the red. In behavior. That's the graph. I know it's time for a break, Mr. Professor. Ooh, no more graphs right now, please. No, because these things will wear you out. You guys, we're gonna take a break. We'll get back to this and finish this up.